The addition reactions in alkynes are electrophilic in nature due to the availability of loosely held pi electrons. As alkynes contain a triple bond, during an addition reaction, they add two molecules of dihydrogen, halogen, or hydrogen halides to form a saturated molecule. Vinylic cation is formed as an intermediate during the addition reaction of an alkyne. Whereas alkyl carbocation is formed as an intermediate during the addition reaction of an alkene. As vinylic cation is less stable than alkyl carbocation, alkynes are less reactive towards the addition reactions than alkenes. Hence, the addition reactions of alkynes takes place under drastic conditions when compared to the addition reactions of alkenes. Let's go through some addition reactions of alkynes. An alkyne reacts with two molecules of dihydrogen in the presence of suitable catalysts like finely divided nickel, platinum, or palladium to form the corresponding alkane. For example, propyne reacts with two molecules of dihydrogen in the presence of finely divided nickel as catalyst to form propane. Alkynes form dihaloalkene when treated with one molecule of halogen and form tetrahaloalkane when treated with two molecules of halogen. For example, when ethyne reacts with one molecule of bromine, it forms 1,2-dibromoethene. And when it reacts with two molecules of bromine, 1,1,2,2-tetrabromoethane is formed. The reddish-brown color of bromine decolorizes due to the formation of saturated 1,1,2,2-tetrabromoethane. Thus, this reaction is used as a test for unsaturation. Alkyne, when treated with two molecules of hydrogen halide, forms gem dihalide. On the other hand, when treated with one molecule of hydrogen halide, it forms alkenyl halide. Addition in unsymmetrical alkynes takes place in accordance with Markovnikov's rule. This rule says that in an electrophilic addition reaction, the negative part of an addendum attaches itself to the unsaturated carbon atom of the molecule having lesser number of hydrogen atoms. For example, propyne reacts with two molecules of hydrogen bromide and forms 2,2-dibromopropane in accordance with Markovnikov's rule as shown here. Like alkanes and alkenes, alkynes are also immiscible and do not react with water. However, in the presence of dilute sulfuric acid and mercuric sulfate at 60 degrees Celsius, alkynes add one water molecule to give aldehydes or ketones. For example, ethyne reacts with a water molecule in the presence of dilute sulfuric acid and mercuric sulfate at 60 degrees Celsius to give ethanol. Similarly, propyne reacts to give propanone. Polymerization is of two types: linear polymerization and cyclic polymerization. When heated in the presence of a catalyst, alkynes undergo polymerization. In linear polymerization, the alkyne molecules form a long-chain polymer. For example, linear polymerization of ethyne produces polyacetylene or polyethine. Polyethine is a high molecular weight polyene which consists of repeating units as shown here. The polyethine molecule is represented as shown. It conducts electricity under special conditions. This is why a thin film of polyethine is used as an electrode in batteries. In cyclic polymerization, alkyne molecules add to each other, resulting in the formation of a cyclic compound. For example, when ethine is passed through a red-hot iron tube at 873 Kelvin, it undergoes cyclic polymerization. In this cyclic polymerization, 3 molecules of ethine polymerize to form benzene. Because of their polymerization abilities, alkynes combine to form many different compounds. For example, benzene obtained by the polymerization of acetylene is used for the preparation of dyes, drugs, and a large number of other organic compounds.